Oh yeah, yeah. If you press G,
Oh, you can draw on it too. Oh my God. All
yeah,
right.
and it actually maps to the surface. Yeah. So let me
Oh,
change it to U
wow.
squared, and we can collaboratively edit it.
That's cool. Nice.
So if you go 5U squared,
Oh, wow. Kind of
What?
dis
When I
kind of disappears off. No, we'll play with this later.
all right. Shall we begin?
Oh, the sky's darkened.
Sorry, what was that?
Oh, the sky's darkened. That's cool.
Yeah.
Yes. All right. So let's get started. Let me just make sure the orb cam is pointing out. We do. How do we do double? Oh, double board. There we go.
Yeah, there you go. Yeah.
There we go. Okay. But I gotta get out of this so I can draw on the board. Okay. Let's clear a few boards. We probably don't need too many today. I'll clear three of them. Cool. So we're up to proposition 3.14 today, and this is a nice proof actually. So it's a proposition of 3.14 is application of Pythagoras' theorem. So in a circle, equal straight lines. So I get these straight lines from a point on the circumference to another point on the circumference. A little bit ambiguous if I just say equal straight lines, but I guess it's kind of clear what they have to be. Equally far from the center. And conversely, the converse is true as well. And I'll just spell it out. Straight lines equally far from the center are equal. So there's a definition I should remind you guys of. What does it mean to be a certain distance from the center? Well, what does it mean to be equally far from the center? So there's a definition, 3.4, says that straight lines in a circle are equally far from the center when the perpendicular lines drawn from them to the center are equal. Perpendicular lines drawn from the center to the line, I guess, are equal. Cool. So I guess this time we have to draw the picture on the next board. Right. So the proof is, as I said, that the application of Pythagoras' theorem, and you see the right angle triangles appearing. You probably already see it from the definition. So there's a circle, and we've got lines. Well, there's a center here. I'm going to call it E. And remember that we can find the center using proposition 3.1. And we're going to have two lines like this. So I'm not going to say that they're equal or not at this point because we're proving both directions. So I'll just draw the diagram. So I have two lines on the circle. I'm going to call them AB, CD, right? And of course, by the definition of equally far from the center, we need to drop perpendiculars from the center to these lines. And so we're going to do that. And there was a proposition 1.12 that allows us to drop perpendiculars from a given line, from a given point to a given line. So let's do that. And this week, we don't have to cheat with our pictures. We can just draw them. We don't have to, contour the picture that are somehow mangled because we're trying to, make a picture that's impossible. Yeah, so we can just join them. Well, actually, my picture's not very nice. Okay, so these are perpendicular lines, and the proposition 1.12 allows us to, construct. I'll just put arrows there. We don't need to do many more constructions, so that's okay. And we're going to call these points where the perpendicular meets our original lines, F on AB and G on CD. So that's it for the construction, and we can go and start the proof. I'll do it on the next board. I guess I drew a rather large circle, so let's move over a bit. Did I? Wait, why is it all following?
You walked a bit far from the board.
Oh, okay. Things are not at the board anymore. There we go. Cool. Okay, so the proof goes like this. So we first assume, so we've proved the forward direction first. So we first assume that AB is equal to CD. So we assume the lines are equal, and we have to prove that they're equidistant from the center, which means we have to show that EF and EG are equal. Okay, so by proposition 3.3, I've noticed that, Dan, you've been using Roman characters or numerals for the book numbers. Maybe I'll do that too. 3.3, EF cuts AB in half. And I guess I won't remind you what the proposition says exactly this, right? If you drop a perpendicular from the center to a line in a circle, it just cuts it in half, right? And conversely. Right? And similarly, oh, that's a terrible similarly. EG cuts CD in half. That's just the other line, right? So same reasoning. Okay, so since AB and CD are equal, we've assumed this, right? I'll just write it again. AB is equal to CD. We have AF is equal to CG. And remember, AF is just half of AB, and CG is half of CD. If AB and CD are equal, so half of the respective lines are also equal. Okay, so next, well, we're looking at those triangles, right? You can already kind of see where we're going. We've got the triangles EFA and EGC, the only two triangles on the diagram, and we're just going to apply Pythagoras' theorem on this triangle. And of course, we have to show that some of these corresponding edges are equal. And so next, EA is equal to EC because E is the center, A and C on the circumference, and these are both radii, right? So as both radii of the same circle. Okay. All right. So we've got two triangles, a bunch of matching lines that are equal. We apply Pythagoras' theorem, and of course the remaining side will have to be equal. So that's essentially the rest of the proof. So I'll write this out. So by construction, EFA is a right angle because we drop the perpendicular. So we get ourselves a right angle triangle. Right, and so we can apply Pythagoras' theorem. Which is proposition 1.47. And to give us EA squared is equal to AF squared plus FE squared. Okay, let's just check. EA is indeed the line opposite the right angle, so that's the hypotenuse, so that's good. And similarly, we do it for the other triangle, and we get EC squared is equal to CG squared. CG squared plus GE squared. And of course, we just established that these two are equal and these two are equal. And so, of course, the remaining term has to also be equal. Hence, FE squared is equal to GE squared. And actually, I don't remember whether we ever proved that positive square roots are equal, unique and right. So,
well, I mean, by this, yeah, that's interesting. I mean, the squares mean the figure, right?
the figure, right?
So that's the area. So it's simply the question of,
Is there another? Yeah.
If two squares are the same, are their sides the same? Yeah, I think this may come down to the technicalities of what the same means.
Right.
Because one way it's simply that the square erected on lines that are the same, and the other way it's like to do with what you mean by areas being equal, which is like rearranging subdivisions or something, but maybe is a little subtle. So yeah, that's a good question. It's not obvious to me its result. Yeah.
Yeah, so I guess I didn't come up with a way to resolve it, I guess, when I was reading it before. But I did flag this and I was like, there's a square root going on. And, we...
Wait. No, you can do it by contradiction. So suppose one of them is longer, then you can erect the smaller square.
Oh, yeah, you can. Yeah, you can put it inside, right? It's completely enclosed in the other square. Yeah, okay. We can do it in the Euclidean way.
Yeah.
Cool. Thanks, Dan. Okay, so the converse is actually, let me just check the OrgCam. The converse is actually just the same proof, right? Essentially, the argument doesn't require any innovation. It's really just the same diagram. We just use Pythagoras in a slightly different way, and then we're done. You can even argue it's the same way. So conversely, assume. Oh, my handwriting's gone off the rails. Assume the conclusion from the previous, right, GE, right? So the lines are equidistant from the center, right? So we still have AEA is equal to EC because these are just radii, right? I'm just going to put radii. And then, the radius doesn't depend on the respective lengths of AC, AB, and CD, right? So then we can apply Pythagoras again. So again, by Pythagoras, we get AF squared is equal to CG squared. So I won't write down the formulas again. It's really just the same formulas, but this time, go back to the previous board. We're saying that, let's erase these. We're saying that these two are equal and these two are equal. And so, of course, AF and CG are now equal. So it really is the same argument, just on different terms of these two equations coming from Pythagoras' theorem. And again, right, by the same reasoning as before, right? So AF is equal to CG. I keep writing G when I meant CG. And so the only last step that we need is that AF and CG are just half of the lines that we're talking about. And so, so we still have AF is equal to FB. and CG is equal to GD. And so AF is equal to FB because it bisects the line, and CG is equal to CD, and so AB is equal to CD, and that's it.
Nice. All right. My iPad's taking a moment to get in. That's the end of the proof, right?
Yeah, that's it. That's the end of the proof. I put that square, probably should have put it at the end of the line instead of here.
Okay, I'll attach a speaker.
Let me go.
Okay. So proposition 3.15 says of straight lines in a circle, the diameter is greatest and of the rest, the nearer to the center is always greater than the more remote. One effect of reading Euclid is that I have available a much more bombastic style for stating mathematical facts. So I'm tempted often in calculus tutorials to speak in a more Euclid way. the greater, the more remote these kinds of constructions. I think they sound very dignified.
Yeah.
Glad to be able to have this style available. Okay, so A, B, C, D is a circle. I'm not going to mark A, B, and C and D yet. So I'm going to mark not B and C anyway. I'm going to mark a diameter, AD. So the claim is that among lines drawn in the circle, this is the greatest that is possible. E is the center, BC be nearer to the diameter AD. So here. And FG more remote. Now we know what that means from what Kenneth just said. Right, the lines that, well, we also know that those lines from the center bisect these line segments by earlier propositions. Those lines are greater or lesser. That's what we mean by more remote or less remote. So we say AD is greatest and BC is greater than FG. I won't write it. That's the goal. Okay, so from E, let EH and EK be drawn. Perpendicular to BCFG. Right, as indicated. Since, well, I'll just state the conclusion. So by construction, or by hypothesis rather, EK is greater than EH. Let EL be made equal to EH. So that is So EK is greater than EH, so we can cut out from it the same length. So EL is equal to EH. Let LM be drawn at right angles to EK. And then do the obvious thing. Continue that line through to N. And then we're going to join ME, EN, FE, EG. All right. Since EH is equal to EL, BC equals MN. Right. That's by what we just did. So that's this length and that length. And since AE equals EM, because they're radii, and ED equals EN, let me find them. But ME, EN are greater than MN by proposition 20 of book 1, and MN is equal to BC. I'll just write it like this. So that is greater than or equal to MN, and MN is equal to BC. So that shows that AD is greater than or equal to BC. Okay, so that's the first claim, that any line is at most the diameter. And the second claim is that BC is greater than FG. So since let me think for a sec. Yeah. So since MEEN equal respectively FEEG, right? Because they're all radii, and the angle MEN is greater than FEG. The base N is greater than FG. So that was proposition 24, book 1. But MN equals BC. So BC is greater than FG.
Oh, nice.
That's all we had to show. Yeah. Yeah, I enjoyed that.
Yeah, that's nice. To move it over the other side and use the angles.
Yeah.
Yeah.
One of my favorite things of Euclid is the interplay between proving things about lengths and proving things about angles, right?
Yeah,
very satisfying.
very nice.
Cool. Yeah,
cool. We're right on time.
Yeah. All right.
Awesome. Thanks, guys, for coming.
Yeah. See you next week.
See you next time. Bye-bye.